The question we need to answer at this point is, how can we assign truth value to more complex formulas? So we have created valuation functions that assign a truth value 0 or 1 to each atomic proposition, to each atomic formulas, and we need to extend this valuation function so that it can tell us the truth value of more complex formulas that contain the connectives not for negation, the connective and for conjunction, the connective or for disjunction, and the connective implies for implication. Let's begin with negation. Now, in the case of negation, what negation does is essentially to invert the truth value of the formula that is being negated. And we can see this quite clearly from this table here. This is called a truth table. This is the truth table for negation. Now let's suppose that we are assigned the truth value 1 to the formula phi. And remember, phi is this Greek letter that stands for any arbitrary formula. If we assign the truth value 1 to the formula phi, then negation of phi will be 0. On the other hand, if we assign the truth value 0 to the formula phi, then negation of 1 will be 1. So this means that negation simply inverts the truth value of a formula. It turns it. If the truth value of phi is 1, then negation of phi is 0. If the truth value of phi is 0, then the truth value of not phi will be 1. At the bottom here, you see again another truth table is the same as the truth table above, is just a shorter version of it. What is interesting is that negation behaves like a function, and in particular, it behaves like the one-place function 1 minus x equals y. To see this, let's consider this function 1 minus x equals y. Suppose we assign to x the value 1. Now 1 minus 1 is 0. Suppose that instead, so if we assign to x 1, then the value of y is 0. If we assign to x the value 0, then 1 minus 0 is 1. And so you see that the representation of this function is exactly the same as the truth table right here. So we can say that the negation behaves like the one-place function 1 minus x equals y. Let's move on and consider the case of conjunction and disjunction. So let's start with conjunction. So conjunction is this connective that represents and. So suppose we have assigned the truth value 1 to phi and the truth value again 1 to psi. So phi and psi are our arbitrary formulas. So if we have assigned a truth value to the two of them, then the truth value of the conjunction will be 1. So if both of them have value 1, then the conjunction of phi and psi will also have truth value 1. However, if we have assigned 1 to phi and 0 to psi, then the truth value of the conjunction will be 0. Similarly, if we have assigned 0 to phi and 1 to psi, the truth value of the conjunction will again be 0. And if we have assigned 0 to both, then the truth value of the conjunction will be 0. So this suggests that a conjunction, so a statement of the form phi and psi, is true only if both the components, both the conjuncts, phi and psi, have truth value 1. Now, interestingly, the conjunction and behaves like a multiplication, and in particular it behaves like the function, the two-place function x1 times x2 equals y. And we can check this, because if I write 1 times 1, then what I get is again 1. If I get if I write 1 times 0, what I get is 0. If I write 0 times 1, what I get is 0 again. And if I write 0 times 0, what I get is 0 again. So in a sense, we can see that the truth table for conjunction that we see here is quite similar to the representation of the function for multiplication. So the value of this function 1, 0, 0, 1 are the same as the value that we get here for the conjunction. I leave it up to you to check that the conjunction behaves very similar to this function min, and the function min is, the min stands for minimum. It's a function that picks the minimum value among the value assigned to x1 and x2. Let's now consider the case of disjunction. Disjunction, as you know, is symbolized by this symbol here. And what you see here once again is the truth table for disjunction. If we have assigned the value 1 to both psi and phi, then the truth value of the disjunction of the two is again 1, and this is the same as in the case of conjunction. The difference is that if we have assigned value 1 to phi and value 0 to psi, the truth value for the conjunction of phi or psi is again 1, whereas in the case of conjunction it was 0. Similarly, if we have assigned 0 to phi and 1 to psi, the truth value of the disjunction of the two is again 1, whereas in the case of conjunction was 0. And finally, if we have assigned 0 to both phi and psi, then the truth value of the disjunction of the two is 0, and this is similar to the case of disjunction. So the meaning of disjunction is that a statement that is a disjunction, a formula that is a disjunction, is true if at least one of the two component of the disjunction, called disjunct, is true. So it's not necessary that both of them are true for the disjunction to be true. So that's the difference between conjunction and disjunction. A conjunction of two components, of two conjuncts, is true only if both conjuncts are true. Whereas a disjunction is true if at least one of the two disjunct is true. It's not necessary that both of them are true. Although it is true if both of them are true, but that's not required for the disjunction to be true.